If you think a container is a virtual machine, that's wrong and it will bite you in production system. By the end of this video, you will run your first container and understand it the way architects do. Welcome to the kingdom, DevOps AI kingdom. Today, we begin the journey, becoming a DevSecOps architect. We start with Docker, but not like everyone else. New theory marathon. We build 100 real Docker images, one per video, command by command. Let me tell you why this series is 100 images and why if you follow it, you will think like an architect, not just pass an interview. Most Docker courses are theory, slides, diagram. Trust me, it works. You finish them and freeze the first time something breaks in your production system. We are doing the opposite. We build 100 real Docker images, one per video, line by line, command by command. I don't skip a single flag. Every command you will know what it does, why it's there, and what breaks without it. And it's never just Docker. From image one, you work like a real engineer works. Git on every video, commit branch, push like a team does. Observation tools on every image, lazy docker, ctop, dive. You will read logs and inspect layer on everything we build. Because an engineer who can't read logs is a blind. DevSecOps baked in. We scan our images, sign them, harden them, slime them from gigabyte to megabyte with multi-stage builds and layer thinking. Monitoring CI/CD, registries, even AI containers, every tool an architect touches, we will going to touch it. Every 10th image is a boss image, and underneath all 100, one real system we will create a secure banking platform. So every image you build plugs into something real. Image 1 makes you a beginner who understands Docker. Image 50 makes you dangerous person. Image 100 makes you an architect. Not because I said so, because you built it. Let's start. Before we build our first Docker image, we owe ourselves 10 minutes of truth. Firstly, what is Docker actually? Not the marketing line, the real machine. I will keep every word simple, but by the end of these slides, you will understand Docker deeper than most people who are already working in DevOps today. And then we will build. Every technology exists because of a pain. So let me show you Docker's pain. Every technology exists because of a pain. So let me show you Docker's pain. We have a developer who writes code on a laptop. The laptop has Python 3.12, all the libraries installed, all the right settings. Then the code works perfectly. Then the code developer sends the code to the test server. But the test server has Python 3.8 and some libraries are missing. So the code crashes. The operation teams fixes that and ships the code to production. But the production runs on a entirely different version of Linux with different configuration. It crashes again. And now the developer says the most famous sentence in all of software. It works on my machine. Here is the real problem. The problem was never the code. The problem is that the environment around the code, meaning the operating system, the libraries, the settings, is slightly different on every machine. The code travels from machine to machine, but its environment does not travel with it. Docker exists to kill exactly this problem. So here is what Docker actually is. In one sentence that you can say in any interview, Docker is a platform that packages an application together with everything it needs, meaning the code, the runtime, the libraries, and the settings, into one portable unit called an image. And then it runs the image on any machine as an isolated process called a container. That is the whole definition. Docker packages and Docker runs. Even the same Docker comes from shipping. Before standard shipping container existed, loading a ship took weeks because every box was a different shape and size. Then the world agreed on one standard container size, and the global trade change, changed forever because the same box fits on every ship, every crane, and every truck. Docker did exactly that for software. Your application goes into a standard box, and that box runs identically on your laptop, on the test servers, or in production systems, or any of the cloud. The environment now travels together with the code. So it works on my machine finally becomes it works on every machine. Now, the number one misconception in this field, and the interviewers loves to ask about it. People think a container is a small, vast virtual machine, but it is not. Look at the two diagrams on this slide. On the left side, you see virtual machines. On top of the hardware and the host operating system sits a piece of software called a hypervisor, and then top of that hypervisor, every single virtual machine carries its own full guest operating system inside it. That is gigabyte of operating system per virtual machine, and each one boots up like a real computer, which takes minutes. Now look at the right side, containers. There is no hypervisor anywhere. There is no guest operating system inside the box. Every container is simply a process, a normal running program on the host own Linux kernel wrapped in isolation. That is why a container is megabyte instead of gigabyte. That is why it starts in milliseconds instead of minutes. And that is why you can run hundreds of container on one laptop. Here is your interview line, word for word. A virtual machine virtualizes the hardware and boots a full operating system, while a container virtualizes only the operating systems and shares the host kernel. Now now let us open the machine itself. Docker is made of 5 pieces, and once you can see these 5 pieces, every Docker command you ever type will make sense. Piece number one is the client. That is Docker command in your terminal. It is only a messenger. It does no real work by itself. The piece number two is a daemon, a program called dockerd. It is a server that runs in background of your machine. The daemon is the engine. It builds image, it runs container, it manages everything. The client sends your command to the daemon over a REST API, which is the same kind of API that web applications uses. Piece number three is images. An image is a frozen blueprint of an application together with its whole environment. Now, piece number four is containers. A container is a running instance of an image. It is a live process, not a VM. It is a live process. And piece number five is the registry. A registry is an online store full of images, like an app store for software. Docker Hub is the most famous one. So, the flow of every single command you will ever type is this. You type the command, the client send it to the daemon, and the daemon does that work on the images, on containers, or on the registry. Now, let's deep dive. Let us zoom into the two most important pieces, the client and the daemon. The client is the Docker program installed on your machine. When you type docker run, the client does exactly three things. It converts your command into an HTTP request. It sends that request into a socket, which on Linux is the file slash war slash run slash docker.sock. And then it prints whatever answer the daemon sends back. That is everything the client does. The daemon is the program named dockerd. where the letter D at the end stands for daemon, which means a background service. The daemon listens on that socket and does all the real work. It builds the image, it starts, it stops the container, it creates networks, volumes, and it pulls and pushes images to the registry. And here is live proof that the client and the daemon are two separate programs. If the Docker engine is turned off, the command docker dash version still works because the client is just a file sitting on your disk. But the command docker ps fails with error, cannot connect to Docker daemon. We will see this demo later. But because there is a nobody home to answer the request, it throw an error, cannot connect to Docker daemon. If you ever see that error, you now know exactly what it means. Your engine is not running. Start Docker desktop or obstack if you are on Mac like me and you are back in business. One bonus fact that architects know is that because the client and the daemon talk over an API, they do not need to be on the same machine. Many times interviewers ask, does the Docker daemon or Docker client are on the same machine? They are not. They talk over API. So the client on your laptop can control a Docker daemon running on a server on the other side of the world. Now we go one level deeper into the part that most courses never show you. Here's the surprise. The daemon does not run your container either. Inside the engine, there is a relay race with three more runners, and their names are container D, shim, and runc. It works like this. When the daemon when the daemon dockerd receives your command to run a container, it hands the job to a program called container D. The only job of the container D is managing the container's life cycle, meaning create it, start it, stop it, and delete it. Then the container D starts a tiny helper process called a shim, one shim for every container. And the shim calls the final runner, a program called runc. Runc is what we call the runtime. And the runc is the one that finally creates your container process. And then here is the strange part. Runc immediately exit. It is done in milliseconds. The little shim stays behind as the parent of your container, holding its input and output. Why is it designed as a relay like this? There are two reasons for that. Reason one is standards. runc follows an open standard called OCI, the Open Container Initiative, which means any tool in the industry can run any standard container image. There is no vendor lock in. Reason two is resilience. For example, Kubernetes, the biggest container platform in the world, talks directly to container D and skips Docker D completely. That is why when you heard that Kubernetes dropped Docker, nobody's container actually broke. And because the daemon is not the parent of your containers, the daemon can even restart without killing them. Do not memorize all of this today. Just remember that the relay exists. Client, then the Docker D, then the container D, then shim, then runc, and finally your process. We will dedicate a full deep dive episode to this after image number 10 we created. Now the question arises. So what does runc actually do to run a normal process into so-called a container? It uses two features of Linux kernel, and these two words answer half of all Docker interview questions. So say them with me. Feature one is namespaces. These are not normal namespaces, these are Linux namespaces. Namespaces decides what the process can see. The process gets its own private view of the file system, its own private network, its own private list of processes inside the container. Your application genuinely believe it is a process number one on its own private machine. The feature number two is C group, which is short for control groups. C groups decides what the process can use. At most, this much memory, at most, this much CPU. And if the process crosses its memory limit, the kernel kills it. That, by the way, is the famous exit code 137 that you will someday see in production, and now you already know about, what it means. So remember it like this: namespaces control site and C groups control strength. A container is just like a normal Linux process wearing these two pieces of kernel clothing. There is no hypervisor, no guest operating system, and now you fully understand why container starts in millisecond, because there is literally nothing to boot. Docker has three big nonces that you will use every day: the images, the containers, and the registry. Let us define all three, one slide each, starting with the image. An image is the frozen blueprint of your application. It contains your app plus its entire environment, packed into layers. Each instruction in your Docker files adds one layer. The base operating system files are one layer, your installed dependencies are another layer, and your application code is another layer on top. These layers are read only and they are shared. If 10 different images all use the same Alpine Linux base, that base layer is stored on your disk only once. An image never changes after it is built. You do not edit an image. You build a new version of it instead. That is exactly why we give image version tags like Hello Kingdom 0.1, 0.2, like that, because we cannot edit the images once it's built. We will create the new image. Here's the analogy we will use for the whole series. The image is sealed cake mix. The ingredients are logged inside. It produces the same cake every single time, and you can share the box with anyone. The second big noun is the container. A container is a running instance of an image. It is an image brought to a life as one isolated process. When a container starts, Docker adds one thin writable layer on top of the image read only layer. That writable layer is the container scratch space for temporary changes. And the image underneath never changes at all. Two golden rule about containers. Rule number one is one image can run many containers at the same time. One cake makes many cakes, and every cake is independent of others. Rule 2: a container lives exactly as long as its main process lives. When the process ends, the container stops. But it does not vanish, it sits there in a status called exited. And the command docker ps dash hyphen a shows you the complete history. You will see that with your own eyes in few minutes. Now the third big noun is the registry. A registry is an online library of images. It is the app store of container world. Docker Hub is the big public one with millions of ready-made images, Nginx, Postgres, Python, Redis, all of them one command away. The command docker pull downloads an image from the registry to your machine. The command docker push uploads your own image to the registry. Companies also run private registry for their internal images. And in the series, we will use all the big ones. AWS has ECR, GitHub has GHCR, enterprises use Artifactory, At image or when we build image 61, we will even run our own private registry inside a container. For now, here is our plan. Image 1 through 9 stay 100% local on our own machine. Your very first push to Docker Hub happens at image 10, where registries get their own full lesson with accounts, tokens, tags, digest, all explained properly. Now let us put the entire machine together using one single command and follow the journey of Docker run from beginning to end. There are 8 steps on this slide, and you already understand every piece involved. Step 1 is you type docker run hello kingdom. Step 2, the client wraps your command into a REST request and send it to the daemon. Step 3 is the daemon checks, do I have that image locally? If yes, it continues. If not, it pulls the image from registry layer by layer. Important, layer by layer. We'll see when we create a Docker image. Step 4, the daemon hands the job to container D and says create and start this container. Step 5, container D spawns a shim and a shim calls runc. Step 6, runc creates your process, reps, namespaces, C groups around it, and then exit. Step 7, your application is now running as one isolated process. The container is alive. And the step 8, when your application process ends, the container stops and it's up and exited in your list. This is everything Docker does end to end. Believe me when I say it, you now understand this machine better than many people already working in the field. Let's recap before we deep dive into building images and go deeper into Docker. Let us recap everything in 9 short lines. Count them on your fingers. First, Docker package applications together with their environment and run them anywhere. Second, the client is the messenger. Third, the daemon is the engine. Fourth, container D, shim, and runc are relay inside the engine that actually starts your process. Five, namespaces decide what a container can see. Six, C groups decide what a container can use. Seven, a image is a frozen layered blueprint. Eight, a container is that blueprint running on one isolated process. Nine, a registry is the app store where images live. If you can say this 9 lines, you can already talk about Docker better than most people in this industry. But knowing is not our style in this kingdom. Doing is. So enough theory. Let us build image number 1, hello kingdom, to the terminal.